Welcome to this podcast on break-even analysis of two alternatives. First, we summarize an approach to identify and solve for a common parameter or variable between two mutually exclusive alternatives. We will use the terms parameter and variable interchangeably. Then an example of a make-buy decision demonstrates the method using manual and spreadsheet solutions. Let's get started. By definition, break-even analysis is the equating of two relations and the solution of one unknown parameter that is common to both relations. For two economic alternatives, we must set a present worth, annual worth, or other relations equal to each other and solve for this common parameter. We can use any measure of worth as the basis for computation. However, using the annual worth or AW method is recommended. In this way, the different life, the equal service requirement, and the multiple root problems that are present in either the present worth or the rate of return methods are all avoided. All relations must be expressed in the same units. Usually this is in terms of money units per year, for example, dollars per year or euros per year. On the left is a graphical presentation of the situation. Two alternatives with linear total cost, or TC, relations are plotted against a common variable. Where the lines cross is the break-even point. For cost-only relations, the decision depends upon the expected level of the variable. Is it above or below the calculated break-even point? In this case, values below the BE or break-even point indicate the choice of alternative 1 because the costs are lower. If the value is above the break-even point, alternative 2 is the choice. These are the first two of 3 steps to set up and solve for the break-even point. First, we would identify the common parameter and its units. The units are important because the components of the total cost, or TC relations, will have to be dimensionally correct. An incorrect answer for the break-even can easily be obtained if the units are not correct, especially for the variable cost, or VC, portion of the total cost relation. The second step requires that the equivalency relations be developed using the common parameter. As recommended earlier, using an AW relation over the respective lives of the alternatives is the easiest approach, but any basis will work provided the requirements of the method are followed. Once the AW relations are equated, solving for the common parameter value identifies the BE point between the alternatives with the time value of money already considered. In order to select one of the mutually exclusive alternatives, the anticipated value of the common parameter must be estimated. If this value is below the break-even point, always select the alternative with the steeper or larger slope. This is the same as the larger variable cost. Here are two linear total cost relations for alternatives A and B, with their break-even value shown. Alternative A has the larger variable cost or steeper slope to the total cost relation for all parameter values below the break-even point. Now look at all points above the break-even value. The alternative with the lower variable cost is selected here since its cost is lower. In summary, if the parameter is above the break-even, select the alternative with the lower or flatter slope. The approach outlined thus far can be applied to a wide variety of problems to find break-even values for parameters such as the first cost P, the annual operating cost AOC, the expected life N, and rates of return of investment opportunities or interest rates for borrowed money. A very common application of break-even is the selection between purchasing an item externally or making it in-house. These make-buy decisions are vitally important as they determine if something will be made by the company itself or purchased from another corporation. The external source will often be an international corporation that has lower costs for labor, raw materials, transportation, or other resources. In make-buy decisions, the selection guideline is shown here. If the required level of the item is above the break-even point, make it in-house or internally. If it is below, buy it externally. That is, select the buy decision. It is time for our example. The situation is as follows. An item costs $100 per part when purchased externally, but it will require new assets and additional cost if it is made in-house. The make alternative estimates are shown here. $150,000 first cost, $20,000 for maintenance and operation of annual cost, and a life of 5 years. The 5 years will be our study period. Labor costs are $38 per hour, and one part is produced every 2 hours. At an expected rate of return of 12%, we must decide between making and buying the item. Let's follow the 3 steps outlined previously. First, define the common parameter as X with units of parts per year. Next, develop the AW relation for the make alternative over a period of 5 years. The fixed cost component is the AW value of the $150,000 first cost plus the annual maintenance and operating costs. At 12% per year, the make option is minus $61,611 per year. The other part of the AW sub make relation is the variable cost. This VC relationship is dimensionally correct for dollars per year. The labor cost is $38 per hour. Each part takes 2 hours to produce, and multiplication by the common variable X in parts per year produces the units of dollars per year, which is the same as that of the FC component. Finally, equate the 2 AW relations for making and buying. The buy AW relation is simply 100 times X. Solution results in X equals 2,200 parts per year. So what is the conclusion? For all expected values of demand above 2,200, make the item in-house. Conversely, if it's less than 2,200 that are needed, purchase it. To solve this same break-even problem on a spreadsheet, use the estimates repeated here. Initially, we set up the annual cash flows for both alternatives. The setup is shown here with the common parameter of X parts per year in cell B9. We will use this cell during the solution several times. Cash flow for each year requires that the level of X be included. For example, the make option cash flow in years 1 to 5 uses the relation minus 20,000 minus 72 times X, but X appears in our cell B9. Also, the buy cash flow functions for years 1 to 5 is simply minus 100 times X, but again we multiply by B9 where the value for X appears. These functions will result in the same values for the AW relations used in the manual solution. You may want to stop the podcast here to be sure you understand how these 2 cash flow sequences are set up on the spreadsheet. Next, we add the AW relations using the PMT function with an embedded NPV function. The functions are shown here in row 11 for both make and buy options, and the numerical values for X equals 0 are displayed in row 12. To carry out step 3 that equates the AW relations, simply subtract the 2 AW values. The subtraction relation is shown in cell B13, and the number is displayed in cell C13, which we will also use several times in the solution. As indicated here, when X equals 0 units, the difference is minus 61,611. We need to obtain a difference of 0 to solve for the break-even value between the make and buy alternatives. The goal-seek tool on Excel is great for these types of problems. We will force the difference cell C13 to be 0, and we will make cell B9, where the X value is, into the changing cell. The blue and red arrows indicate the cells entered in the goal sheet template. The resulting value will appear in cell B9. It will be the break-even value. The result, when the OK button is clicked, is 0 for the difference, as we expect, in the AW, and the break-even value is 2,200 in cell B9. This is the same value obtained with the manual solution. As you might expect, another benefit with the spreadsheet setup is that any parameter can be easily changed to evaluate the sensitivity of the break-even value to the change. This concludes the break-even presentation. As always, thank you for watching.